Alright, so let's go on. Okay, some of you already got the lectures note from others, from your senior and so on. So maybe this one can be to be a recap lah for you. Okay, are you ready, guys? So if you are ready, please type ready, sir. I'm ready, sir. Okay. Okay, good. All right. This class is not for only for T20, okay? For all T or B and so on, you can join. Okay. Where is it? Okay, for today's topic, lectures 3 is about performance characteristic for measurement and instrumentation system. So for last week we have learned about the measurement. Okay, measurement that means it's a process. Okay, you do some measurement. Okay, so what you want to measure? So we have it 7 quantity, right? Quantities that you can measure, right? Quantity is okay. All right. So first one you can measure, for example, the length. Okay, the length. Okay, and then number 2 you can measure the mass. Okay, and number 3 you can measure the temperature, and number 4 etc. lah, illumination and so on. Okay. So this is the 7 basic quantity, and then from that one you can derive to be what we call it other quantity like area, like what is it, force and so on. Okay, and then we want to do the measurement, and then we need the instrumentation. We need the tools in order to do the measurement. Okay. And in order to select the correct tools, right, for you to do the measurement, so you will look into characteristic, right? Into characteristic. And when you look into the characteristic, you will look into the performance, right? So the performance can be divided into when we talk about the performance, let's say we want to look about the response time, we want to look about the range, we want to look about the accuracy, right? How accurate is it? Okay, and so on. Okay, so the characteristic have a lot, right? So you will have static, right, and so on. Okay, we look into that. Okay, so just to recap back, so what is the instrumentation system? So there are 4 components involved in the instrumentation system. It will be like this one. Okay. So of course, you want to do the measurement. That means you will need a transducer, right? Or sometimes we call it a sensor. So for example, your transducer, it detects the temperature, and then it will convert it into useful value, which is the millivolt. And then you need a signal conditioning to amplify it to become a voltage, right? So this one is SG. SG is not Singapore, guys, right? Okay. Although that you can go to Singapore, but SG here is not Singapore. Okay. So please make sure that they use the green color pump, right? In order to fuel. Yeah. Around 90, we believe that now the price is go like a rocket, right? The price for the petrol. Wow. Okay, so done. SG is for signal conditioning, and a lot of the instrumentation will show the digital value. So if the instrumentation will show the digital value, that means you need the analog to digital converter. Okay, that we convert it, that we sample it, all this analog value, it will convert it into digital value and so on. Okay, so this is the 4 basic component that we need to have for the instrumentation. system. Okay. Alright. Have you ever seen the data sheet of sensor or transducer? When we want to buy the sensor or transducer, for example, if you work at the engineers, right? Like okay. So and then your boss say, hey, I want to do some project. Alright, we have the boiler. So there is some issue that are cracking and so on. Okay. Can you check this boiler? So in terms of the temperature, what is the pressure and so on. Then you try to buy, start to Google, under Google. Okay, what is the sensor or instrument that you can use? So you will look into the data sheet. Okay. So if you look at the data sheet, that means you will look at a few value like, for example, plus minus 0.2x, right? This one is plus minus 0.28 degree, okay? And then what else? Yep, you will have 32 plus minus 50, and then you will have the word accuracy, right? So yeah, we will want to look at the accuracy first. 0.5 to 5 full scale. Okay, what does it mean? Okay, FS. Alright, friendship forever. No, what is it? FS. Okay, and then you, of course, you will look at the pressure range, right? Because yeah, sometimes we don't know what is the range that we want to measure, right? For example, so we will look at the maximum range, for example, okay, and so on. And then you will have the word span, right? Okay, the span, the solution, and so on. Okay, this is what is the data sheet is about. So we can divide the performance, right? The performance into three categories, which is the operational characteristic, static characteristic, and also dynamic characteristic. Okay. So operational characteristic, yeah, it is like you want to look at range, right? Minimum and also maximum. Okay, this is what range. Okay, when you want to operate the sensor, we want to operate the instrumentation, you look at the first is range, whether is meet your requirement or not. Okay, and then the span, right? The differences, this means differences minimum, maximum, and minimum. Okay. For example, you have the thermometer that have range minus 0.5 to 40.5. Okay, right now, and in order to find the span, you just need to guide the maximum you minus with 0.5 degree. Okay, then you will get this guy. So you know, right? Okay, the range it can be until 41 degree. Okay, this is the range from 0 to until 41. And operational characteristic also have the sensitivity. So when we look about the sensitivity, it will refer is the ratio between output and also the input. So sometimes we call it is a transfer function. Okay, so for example, if you buy a sensor, right? So your sensor right now is detect the temperature, and then the output, the useful value will be millivolt. So the sensitivity unit will be millivolt per degree. Okay, right now that's what we call it sensitivity. Okay. For example, a galvanometer has a sensitivity 17 mm per microamp, right? So 1 microamp input, deflection on the scale show a movement of 17 mm. Okay, so for example, this one, we know that the input right now is microamp. Okay, any current that enter to the galvanometer, you will produce in terms of the deflection, millimeter. So the sensitivity will be 17 mm, okay, the output over input microamp. Okay, so anything value that you will have, for example, the current that enter to the galvanometer is the 2 microamp. So it will be 34 millimeter, the deflection of the scale. Okay, so that's what we call the sensitivity transfer function. Okay, and resolution. Yes, resolution, this means the smallest change that it can detect. Okay, so yeah, for example, you have a force sensor measure a range 0 to 150 Newton with a resolution 0.5% full scale. So full scale, that means the maximum value that it can detect, or what we call it, sorry, the maximum range. Okay, the maximum range. So for example, 150 Newton, so this will be the full scale lah. Okay, alright. So in order to find the resolution, so you need to 0.1 divided with 100, right? You need to time with 150 Newton. So this one will equal to 0.15 Newton. So that means the smallest change that it can detect is 0.5 Newton. So if you want to measure something that around 0.10 Newton, so you cannot use this kind of sensor. Okay, all right. So this is what is we will tell you about. Okay, and yeah, for example, this one is 0.1 or 0.2 Fahrenheit. So that means the resolution that it can detect is 0.1 degree. Okay, very accurate one. Okay, so let me ask you a question. If I have a temperature sensor that can detect my body temperature, so I have a 0.5 degree, right? The resolution, right? Is it, you can use it for checking the body temperature, 0.5 degree? Yes, alright. Okay, because our temperature right now 71.1 or 738 or something. It can go what, 36, right? 36 degree and so on. Okay, right. So right now when you go to any mall or any supermarket, you don't need to put your head anymore. Normal temperature. Oh, I missed that one, right? Do you miss that one? Normal temperature. But certain mall like IKEA and so on, they still use to scan the temperature, but they only scan our skin temperature, which is what we call it the thermal temperature. Okay. Alright, so the resolution done, then dead band, oh that, right? So dead band, that's mean where is the largest range or largest value that your instrument that cannot be respond. You will see that maybe we show you the range. For example, the range of the sensor is 0 to 20 Newton. So, and then it will show you the scale will be at the maximum one. Yeah, I cannot measure anymore. Okay, is what we call it, the dead band. Okay. Alright, so this is the operational characteristic. It's about the value of how the instrumentation to be operated. Okay, this is the important thing when you look at the data sheet. Okay, alright guys, is it clear? Clear, right? Simple lah. Okay. Yes, on my radar, good. Okay. Okay, now we look into the static characteristic which be involving accuracy and also error. Okay, this is where you will do your experiment, you will find the error, right? Error between theoretical and also experiment. And then for the discussion, yeah, due to human fault, my friend at that time, he got some problem with his eyes, right? His eyes only have one eye that time. And then that's why I cannot get the accurate value. my friend at that time, he take the reading not accurate, right? I blame him. Okay, why don't you write? That's kind of the discussion, right? On your experiment report. Please write it like that. I will give you the full mark for that section. Okay. Yeah, sometimes when I marking the exam, and not exam, the experiment report, right? It will be the same discussion between you and your friend, between you and your other friend, right? Between you and also the master copy, yeah, right. We as a lecturer also have the master copy for. Okay, please write something joke about it, right? About the error. Yeah, the error big loss is because my friend. That's why when we marking it, we will wow. Okay, I'm happy to mark the experiment. Okay, right. Yeah. Okay, random error. That's mean maybe on term of the environment and so on. Yeah, gross. Yeah, or because of your friends. Systematic. Blame the equipment. Okay. Improper equipment, right? 10 years is not calibrated, okay, and so on. Okay. And then when we talk about static, is it will be involving error and also accuracy. So what is the difference between accuracy and error? So accuracy will show you the maximum overall error exactly that you need to be expected. Okay, you need to be expected. So when you measure the value, right? You measure something. That means the value that you get it is you need to be plus minus with some error. That's mean you know that okay, this is the value. Okay, and so on. Okay, so measured variable. So measured variable, yep. Sometimes the accuracy when you look at the data sheet, right? It will show you difference, right? Different meaning, right? It's not different meanings. It's a different written, right? So for example, like this one, nominal accuracy. Okay, it give you in the unit, right? It give you the unit. And then for this guy, it give you 0.25% full scale. Okay, it depending on the manufacturer. So for this accuracy, when you see that the data sheet it give you is already in the unit. Okay, for example, like this guy in the unit. So the accuracy right now, right? The accuracy, for example, it give you in the unit plus minus 0.2 degree. So now we want to find the error, right? The error right now equal to plus minus 0.2 degree. Okay, so the unit itself you can take it as the error. Okay, so some word error or uncertainty. Okay, what is that? Okay, right. So when you have the measured value, for example, this one 30.1, so actually the real, right, the correct value, right, will be range between 30.3 and 20.1. Okay. Alright, so some of the data sheet also show you plus minus full scale. Alright, so in order this you need to know what is the maximum range. Okay, and then from that one you can find the error. Right, so accuracy equal to plus minus 1 over 100 time with full scale over time 10. You will get a plus minus 0.1 ampere, right? This 1 ampere. So that's mean your error after you get the unit, so you can use this one 0.1 ampere. Okay, this is the difference between the accuracy. The accuracy will be different representation, right? For example, full scale and so on. And some of the manufacturer they put in plus minus percent span. Okay, so you need to find the span first. So this means the accuracy equal to plus minus 3/100 times with span. Where are we going to find span? Okay, 50 minus 20, for example, the maximum minus minimum. Then you get it plus minus 0.9. In this one is PSI. So now you get the error equal to plus minus 0.9 PSI. Okay. And some of that, it doesn't give you the unit. It's only give you only the percentage accuracy equal to plus minus 2%. Okay, so in this case, you need to know about the measured value that you measured. So that's mean the what we call it, the error. Okay, if you measured 2 volts, so that's mean 2, you need to time plus minus 2%. We got it plus minus 0.04 volt. Okay, all right. So this is many type of the accuracy definition in the manual on the sheet. Okay, so far so clear. So far so clear. Operational done, range, span, and so on. Okay, so far so clear. Okay, good. Right, good. Okay, done. So let's move. Oh, example 3.1. This one is quite simple, right? Very simple. Okay. So, you have a temperature sensor has a range 20 to 250. Yeah, this one we can know the full scale of this. A measurement result value is 55 for temperature. Specify the error if the accuracy is. This one is quite simple. So, for the A, accuracy equal to plus minus 0.5 divide with 100 times with 250. Now you get the answer. Okay, will be plus minus 1.25 degree. Okay, so the error will be plus minus 1.25 degree. Okay, so what is the possible temperature for each case? Temperature, so you just 55 plus minus 1.25 degree. Yep, done. Okay, right. And then span, yeah, span is simple. 250 degree minus with 20, 230 degree. Okay, so accuracy from here, accuracy B, then plus minus 0.75 over 100 you time with 230 degree. Now you get it here is what is it? 1.725 degree. Okay, accuracy plus minus. Okay, alright. So that means your error is equal to plus minus 1.725 degree. 25 degree. Okay. Then for the actual temperature will be 55 plus minus 1.725. 725 degree. Okay. Right. Okay. And number 6 of the reading, I think you can continue it, right? It will be simple. Okay, so this one will be plus minus 0.8 over percent you time with 55, right? Then you get the error lah, plus minus 0.44 degree, and then your error between 55 degree plus minus 55 plus minus 0.44 degree. Okay, yep, the temperature. Okay, I think it's very clear. Okay, very clear. Okay. Right. So this is how to find the accuracy first, and then you can find the error. Okay, so guys, have you for the Muslim, have you go to Bazaar Ramadan?
Yes, Prof.
Oh, wow. Where? In the UTM or outside UTM? Alright. Okay. Next to my hostel. Wow. Good. Okay. When Taman Sri Pulai. Ah, yeah, yes. Taman Sri Pulai. Good. Kelang, KLJ. A lot of food, right? You can buy. Wow. Okay. But be careful also, guys. We don't know when we be uh, a victim for the COVID-19. Okay. So right now we already in the endemics, right? Endemics. Okay. It's not the end game yet. Mix. Okay. All right. How about if we only got the information about the transfer function or sensitivity? Okay. Right? And then we are given the accuracy of plus minus 1%. So what is the possible range? The possible range, that means you need to find the error first. Okay, find the error first, and then after that you will find the possible. Okay, possible range. Okay. Okay. So like this one, the temperature. The temperature, okay, it gives you 5 millivolt. The sensitivity or the transfer function, that means the input is degree, the output is millivolt. Okay, so then accuracy, it gives you 1%. Okay, so we can find the error, right? The error of this transfer function. So 1/100 you times with 5, right? The unit in millivolt per degree. Now you will get it. The answer is plus minus 0.005 millivolt per degree. So we know that the error, right, for this transfer function can be from minus 0.05 millivolt per degree to plus 0.05 millivolt per degree. And then, yeah, that is the answer, right? So possible range, okay, possible range. So now it will be plus minus 0.05 millivolt per degree. Okay, yeah, example 2. Okay, and then 3.3. So we know that the possible range is around that one. Yeah, actually this one, 5 plus minus 0.05. Okay. So when we know this possible range, then that means we know this the minimum and also the maximum range. And then what happened to this value, right? We got it this value. For example, we got it the output is 27.5 millivolt. So what is the temperature in this one? We reflect the output 27.5. So you just need to divide it, right? So you get this output, and then you need to divide it here, and then we get it here. Okay, so same thing like this one, divide and you get it here. So for the temperature that we produce 27.5, so the input temperature will be 5.45 degree to 5.56 degree. Okay. This is how when you have only the transfer function, so we can determine the input, or also we can also determine the output. Okay. All right. Okay. So this is the example 3.3. Okay. All right. So the previous example we just talked about only a sensor or transducer itself. So when we talk about the accuracy of the instrumentation itself, so you need to derive some of these formula, right? For example, you have the input that you want to detect, which is the degree, right? And then the output of the instrumentation itself, it can be a voltage, right? And then the transducer itself, it can have the error, right? This one, and over with the k is the nominal transfer function, or sometimes we call it a gain. Okay, and then the signal conditioning itself, it have the error, right? And also it have the k. So what will be the relationship between the output and also the input here? So we will look into this. Okay, so and plus delta k over k and delta g over g, we call it the accuracy of the transfer function. Okay, yeah. So let's do some derivation little bit about this. Okay, so let's derive it. Okay, right. So we have here a v plus minus delta v is equal to c. What you do is you time all, this one time all. Okay, so let's do this. C k plus minus delta k, right? Time with the g plus minus delta g. K delta g plus minus g delta k. Okay, so the last one you will get it is ckg plus minus ck delta g cg delta k plus minus c delta k delta g. So this one, the equation. Okay, so we know that the output, right, will be voltage, right? So it will equal to temperature, which is C, then with the gain K and G, right? This one. And then the error delta V is the error of the output. Okay, so will be equal to C K delta G, actually the plus minus lah, and C G delta K plus minus C delta K delta G. Okay, so this will be the output and then the error. So what it means is you can get it the voltage from your C, G, and also you time with the input. Okay, so in terms of the fractional, right, uncertainties or error per output, you can get it here. Delta V over V, error, right, per output, error per output. So what you get it here is plus minus Ck delta G plus minus Cg delta K plus minus C delta K delta G. So you divided with voltage is Ckg. Okay. Then what do you get it here is the final one is error per output, or we call it fractional certainty. So you got it plus minus delta G over G plus minus delta K over K plus minus with C delta K delta G divided with Ckg. Okay, so this one you can cancel out, right? Because delta K delta G, when you multiply it, is almost will be give you the small value, right? Okay, and then when you divide it with the largest value, for example 100, okay, it will be very, very small, almost zero. Okay. Alright. So the last one, the system accuracy for overall instrumentation, we give you only this one. K over K plus minus delta G over G. Okay, so this is what it's about. Okay. Boleh guys? Boleh? 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 Okay. Alright. Boleh? Okay. Please type boleh. Okay. Najmul Islam, are you a Malaysian or from other country? Najmul? Okay. Bangladesh. Okay, good. Bokeh. What is the bokeh, guys? Bokeh, I think from the, what is it? I don't know. Lantanis? No? Alright, good. So this is the accuracy of the instrumentation itself. In terms of the percentage, yep, you can multiply with 100. Then from this one, you also can find the RMS. Okay. And I don't want to go through the detail. Okay, example 3.4, you want to find the system accuracy. If you have the transducer and also the signal conditioning, what you can find it is the system accuracy will give you, for example, this one we can say that K, yeah, this one is K, and also plus minus with delta K, okay, and this one is G, so plus minus with delta G, okay. So what you can get it is delta K over K, you can get it 0.15, okay, and also delta G over G, you can get here, so you get it, okay. And you need to find the RMS, so just use this formula, you can get it this. Okay, simple like that lah. Okay. Alright, so the last one, precision and accuracy. Yes. So yeah. Wow, Omarida, how do you make the English keyboard like that? You can make the emoji like that. Do you program something in the Webex? You change the coding, right? For the Webex? No. You make the emoji like that. Okay. Alright. Precision and accuracy. Oh, okay. Okay, I know you use phone. Sometimes we confuse. We say that yes, our data is precise, right? Sometimes we just imagine that yeah, precise and accuracy will give you the same meaning. Yeah, but actually it's not. Precise that means how closeness your data is it. Right? That's why we call it precise, right? But it's not exactly will be accurate value. Okay, right? So this is like precise. Okay, the data is precise. It's also data precise, but this one data is not precise. Okay, and this one also data is not precise. Okay, so accurate value that means the true value. Okay, okay, this is true value, right, and so on. So you can have the precise and also the accurate value. And then linearity, that's mean so sometimes when we get our data, so we will analyze it, right? You will analyze it. You want to see the relationship between the output and also the input, okay? And then you start to plot your data, right? And then you start to find the best fit line in order to see the equation or relationship between input and also output, okay? So normally we use the software lah, right? We don't use the hardware to do the flip-flop and so on. Okay, it's quite difficult. And repeatability. Okay, repeatability that's mean yeah, yeah, sometimes when you do the experiment for today, and then when you repeat that experiment for the next week, you will get the same value. Okay, so I have do some the experiment when I just want to check, right? So I have 10 sensor, right? So I put the sensor 1, okay, S1, the sensor 2, sensor 3, and also until the sensor 10. Okay, I just measure it. So this one, so what I do is I just power up the power supply. I put it around 10 volt, and then this is the resistor, 1500 ohms, right? So this sensor will give you the output, right? The output of the current, okay? The output will be in terms of current I, okay? Right. So what I do is when I get the data, for example, for 100 sample or 200 sample and so on, I will get it. I supposedly will get it the same value, right? I supposedly to get the same value for today and also for the tomorrow, right? I will should get the same value lah. If I able to maintain the same operational condition, right? Because our sensor itself, it will affected by the temperature. Okay, right. So this is what I do is if I do not get the same value, right, at the same operation, that's mean my sensor got problem. Okay, right. So I cannot achieve this one repeatability. Okay, whether is good or not, okay, it is depending on how you set up the experiment. Okay, and also the word calibration, yes, very, very important when you develop the instrumentation itself or when you're using the instrumentation itself. So you need to do the calibration, right? Calibration. So do you remember when you have a temperature gun, okay, for example, this one, all right? So how to do the calibration? That's mean you need a standard value, right? A standard value, that's mean, for example, okay, you know that, okay, you have the big cup, right? This one, and then you put some ice, okay, some ice and so on. So when you scan it, you know the ice will give you 0 degree, right? So when you scan it, so your temperature will give you 0 degree, okay, right? If your temperature give you about 1 degree or 2 degree, so it will be something wrong. You need to calibrate your sensor. Or what you need to do is you need to minus with the offset value. What I mean by offset value, for example, this is your measured temperature, which is X, right? Right? I label this X. So you get a temperature at 2 degree, okay? But you scan it at a 0 degree, so you need to minus with 2 degree, okay? So that you can get a 0 degree. So this one we call it is the offset value. Okay, all right. So regarding your project, right? Regarding your project, you will use like LDR, right? So LDR will detect what? Lag, right? Detect lag. Okay. So how are you going to do the calibration? What is the standard material or standard thing that you can use? What is it? Can somebody write in the chat? How are you doing? How are you going to do the calibration or light or intensity of light? Okay. So we have our LDR, right? So LDR will detect. So the circuit may be like this. Okay, this one 10 kilo or this one you put a 5 volt. So this is your LDR. Okay. Yeah. Of course, you can get the voltage from here, right? voltage from here, you can get it, right? Millivolt and so on. But after this, you will convert it, right? So if you get a millivolt is equal to what law? Okay, all right. So how are you going to get this law? How are you to get this value? How are you going to get it? Because you don't have any standard value, right? Any standard equipment or device that can show you, oh, this is the law. Yes, correct. So when I talk about the standard, so it's not about only the material itself. You also can use a material or like material that has mean like ice, right? You also can use the standard devices in the market, for example, the meter or instrumentation in the market, right? For example, right? So what I talk about the meter or devices, that's mean, for example, you also can have the thermometer here, right? The standard thermometer. And then you can compare between your instrumentation with that standard uh, thermometer. Okay. So right now in your case, in lab, right, in order to measure the lab, what you can use is there are a lot of the, yeah, of course you can buy the lab meter. That's one option. The other one is you can use the lab app, right? From your handphone, right? You can download lab app. There are many apps available because uh, actually your handphone also have some kind a sensor that we say the LDR, right? In order to measure light. And you use that kind of app, so you know that okay, when you scan something like, so it will give you the lux value. Okay, so from that one you can use it, right? You can plot it, you can find the relationship between the voltage that you get it from the LDR and also the lux that you can get it from the apps. Okay, that is the simple one lah. If you cluster kayangan, so you can buy the lab meter. Okay, is it clear, guys? Clear? Clear a little bit about your projects? Okay, guys, clear? Okay, alright. Okay, you can ask anything as one to book. Okay, alright. So we only have 10 more minutes. Let's go to the next chapter, guys. Is it okay? Okay, guys. Okay, guys. Okay. All right. We still in the performance characteristic. So we have learned about the operational, range, span, depth band, resolution, sensitivity. So now, and then after that, we learn about static. Static only got accuracy and also error. Okay, and so on. And then next is the last one is dynamic characteristic. So dynamic characteristic, that's mean right behavior on how our sensor or our instrumentation it will behave, right? So whether it will behave as the zero order or it will behave as the first order or second order and so on. So that also need to be considered, right? Need to be considered when you do the measurement, right? You sometimes if you want to get the response very quickly, so you need to know the instrument that you will use. Okay, system time response. Yep, like I said before, we will look about the time response and so on. Okay, so it show the you how the output related to the input if the input is constant. Okay, example is the mechanical switch. Okay, and also yeah, That's mean the mechanical switch, that's mean when you power up, right? You are given a time when you power up, and then it will stay, yeah, it will stay at every time, yeah, it will stay. So, dynamic transfer function is called time response with the output change in time when the input changing in time also. So, let's say you are given a sensor, right, that can detect the degree and also the output is millivolt, okay, and then the input, right, input at that time is 25 degree, and also 60 degree. This one at over time, right? So at the time zero, the temperature is 25 degree, and then after that, it reach at the 5 second, okay, it reached to 60 degree, okay. And how about the output, right, of your transfer function of the response of the output? So maybe at that time, 25 degree it detect 1 volt, and then at the 60 degree it detect 10 volts, okay. But the output will be, yeah, it going slow, right? So like this, okay. It need time, the rise time, right? It need time, okay. Right. So I don't know which one is this, okay. So this is what the behavior, what we want to look at, right, on the sensor. Okay, when we talk about the dynamic relationship between output and input, so we derive some empirical model, so we can look at the how order is it, right, by look at the n value and so on. Okay. Yes, example 4.1. Have you learned about control engineering subject? Have you enrolled? Have you taken the control engineering subject, guys? No? Yes. Okay. No. Najmul Islam, no? Yes. Okay. All right. For example, you have a second order system where we have the mass here, and then output will be the displacement. Okay. Right, S naught, and also input will be Si and so on. When you derive it, right, the relationship between the spring and also the damper, you have the spring and damper here, you will get this one. So by knowing that the orders, right, so this one we know about n equal to 2, so this is will behave at the second order. So the output will be, the output is S naught, right? Second order, that's mean when you set the input, xi, yeah, I set it, I want it move to 1 meter, okay. So output should be moved also to 1 meter, right? I give the input, okay, 1 meter, output should move on 1 meter. This in the input, the response will be like this, right? We push it 1 meter, but at the output, the response will be, oh, I overshoot a little bit, okay, and then I will take time to get the 1 meter, right? So this is the time that we want to know, right, in order to get 1 meter, okay. So this is the dynamic response is about. Okay, by knowing the n order, so we can know that whether our response will belong to the zero, first, and second order. So zero order instruments, right? It is like the potentiometer. So potentiometer, you know that it can measure the angle, okay, the angle of degree and so on. Okay. So what the relationship it will be, right? So the input will be the angle, right? You turn the knob, right? Degree, right? Okay, the unit is degree, and then the output in term of the resistance. Okay, so the changes of the resistance. Okay, you can get it. For example, you turn at 30 degree, so it will give you about 10 kilo ohm. Okay, so but the potentiometer response itself is, it will be static, right? So for example, this is ohm over time, the output, right? So it will be maintained, yeah, 10 kilo ohm, right? 10 kilo ohm over time. Okay, it doesn't change, right? And then the runtime also will be quite fast. Okay, 0 turn. And then the first order there are two parameter that you need to be considered. One is the K, which is the gain, and also T is the time constant. Okay, right? So this is the relationship between this one. So example, or the per order system is like thermocouple. Yes, thermocouple will take time, right? It will take time in order to send the temperature. For example, it send at 20 degree. So now it take time the 60 degree. And you will look the behavior of the first order, it will have the transfer function T, right? T, right? Capital T. Okay, it's not the time. Okay, it's about time constant. So in order to find T, that means is 63% of final output. Okay, so if your final output is 60 degree, so that means 60% of the 60 degree, right? Time with the 60 degree. So what is this value? Okay, so this value will refer to this, and when you measure the time constant, will refer to this. Okay, so the time constant is at this one, is not at this one. Okay, this one is not at this one. Okay, and characteristic of the first order system. Okay, so you will have the time constant here, right? And then this one is second time constant, and third time constant, and fourth time constant, and so on. So how to get time constant? That means 60%, 63 over 100. The final output is 1 times 1 is 0.63. So that means is over 0.63. Then you can get it here, time constant. Okay. And the second one, 2, 3, 5, and 10. So my question is, when you have the sensor that behave like this one, right? Which point that you should measure the data? Which point that you should record the data? At which stage? Is it T, 2T, 3T, or 4T? Okay, which one? Or you have the 5T and 6T. The data that you get it will be accurate. Is it this point you get the accurate data? Is it this point you will get the accurate data? Or this one you get the accurate data? Or at this one? Which point? Guys. Yes, correct, Zuhair, correct. So that means when you want to get the data, right? So you need to wait at this one. More T, right, will give you accurate data. Okay, all right, because it's more close to the final value, right? So this one we can get the steady state error between the true and also the measured value. Okay, so for the sorry guys, I will take about 5 more minutes. Okay guys, boleh Okay, so start input then respond. So what we have here is we know that the first order response will be behave like this one, right? Okay, so in this one we will have some, we call it the time constant. Okay, time constant at the 63%, right? Okay, 63% of final of YF lah. Okay, final. Then you will have this kind of formula, right? The initial value plus with the final value minus initial value, and then 1 minus E minus T over time constant. So 1 minus E with time constant will show you this kind of graph. Okay. Okay. So let's go to example 14.4.2. A sensor measured temperature linearly with a transfer function of 33 millivolt per degree and has 1.5 time constant. So this one we know that the time constant equal to 1.5 second. Find the output of 0.75 second after the input change from 20 degree to 41 degree. So when we have the time constant, so we can get the output and so on. Okay. Alright, so we derive first. Now we can have the graph like something like this, right? We have these two graphs. One is the input and the other one will be the output. So input right now temperature, so we can put the temperature over T. Output is the voltage, right? We can put it like initial, like Y, and T, the output. Okay, so the input change from 20 to 41. So this one is 20 and this one is 41. Okay, so the graph, because it's the temperature, right? We need some time lah. Okay, this one. Okay, and then the output will be Y initial and also this one Y final. So because of the behave of the input like that, so the output also will be like that. Okay, right. Okay, so this is the graph. Okay, and then we know that the formula will be YT, Y initial plus Y final minus Y initial time 1 minus E minus T over time constant. So the question is find the output of 0.75. So that means find Y for 0.75. So what is it? Okay, that's the question is about. Okay, all right. So it will be quite easier. So what you need to do is you can find the Y initial first. So Y initial is 33 millivolt per degree. UV time with 20. Now you can get the Y initial is 600 millivolt, right? So this one is 20 degree, right? Then you time with this guy, you get the initial. And then Y final is about 33 millivolt per degree. You time with 41, then you can get it 1353 millivolt. Okay, so that means the Y initial is 6300. Okay, millivolt, and Y final is 1353 millivolt. Okay, so that means you can get it here 6300 plus 1353 minus 660 minus E minus 0.75 over with time constant 1.5. Okay, so the final one that you will get it here is about 932.7 volt. Alright, I think it will be simple like that lah. Okay, it will be simple like that. And then example 4.2, when you get this output, so what will be temperature? So you just divide it lah. So you get it this one. 28.3. What will be the error? So you just minus true value 41 minus with 28.3. Okay, right. This is the example of the first order system, and then the second order, yep, when you have this n value and so on, so it behave like that. But the second order will be not covered for in this what we call it in this subject. Okay. So example, the second order is the accelerometer. Okay, it depending on the damper value and so on. Alright, so the last one is the reading exercise. So yeah, what is the standard deviation? Yeah, we have learned about last week before. So what is the three type of performance characteristic? We have three: operational, static, and also dynamic. Right? So what is the process flow to know the performance characteristic? So first of all, we need to know about our requirements. So we need to know about the range and so on. After that, we do the measurement, so we need to do we need to know about the error accuracy and so on. And also after that, when we do the some measurement, we get the response, right? So on that time we need to know about the dynamic characteristic. Okay, so the important to know the performance characteristic of instrumentation system. Yeah, this is based on your logic answer, right? Important to know. All right, for example, you want to know yeah, in order to control or to monitor and so on. Okay, yeah, something about it. Okay, so I'm sorry guys for taking take time for 5 minutes, but okay, so that's it for today class. Okay, guys, hopefully you can enjoy, you can get it on my class for today. Okay, all right, and I will see you again on this Sunday, right? This Sunday is not holiday, right?